Institute of Technology. I, Uday Nikam, welcome you all for the first session of fifth day. Today is the fifth day and 5th September also, and we celebrate 5th September as a Teachers' Day in our country. So happy Teachers' Day to all of you. I feel privileged and honor to welcome.
Happy Teachers' Day, sir. Good
Yes,
morning.
yes, good morning. I feel privileged and honored to welcome our guest speaker for this session, Dr. Hemavathi. I wish Happy Teachers' Day to our guest madam, Dr. Hemavathi.
Thank you.
Yes, ma'am. Before the start of the session, I would like to introduce her briefly. Currently, Dr. Hemavathi is working as the scientist at CSIR's Central Electrochemical Research Institute in Chennai. She is working there from 2018 till date. The institute comes under the Ministry of Science and Technology, Government of India. Prior joining to CSIR, she worked as the project associate at the Central Power Research Institute, Bangalore. She worked as an electrical engineer at Yashika Industries, Chennai, and at Santriya Technologies, Chennai. Dr. Hemavathi has worked as an assistant professor also. She worked at Karpaga Vinayaga College of Engineering and Technology, Chennai. She worked there from June 2014 to November 2015. Dr. Hemavathi completed her master's in power science, power system engineering from Annamalai University, Chidambaram in the year 2014. She completed her BE in electrical and electronics engineering from Anna University of Technology, Tiruchirappalli in the year 2012. Madam has a wide scientific interest. I mention it briefly. She has interest in solving and analyzing the circuits simulation, control system design and stability analysis, design and development of battery management system. Madam has research interest in design, integration, and prototyping of batteries and packs for energy storage. She has interest in electric vehicles and consumer applications. Dr. Hemavathi has worked on projects with the role of principal investigator funded by CSIR. She worked also on another project as the project associate funded by CPRI, Ministry of Power, Government of India. Madam has presented research papers in national and international conferences across the India. Her research papers have been published in renowned science and IEEE journals. I'm truly honored to introduce you, ma'am, for this session. Once again, very warm welcome to you, and I request you to begin with the session. Over to you, ma'am.
Thank you. Thank you for your brief introduction. Okay, so good morning to everyone. First of all, so happy Teachers' Day, everyone. Okay, so
thank you, ma'am.
Yeah, thank you. So first, I'm going to share my presentation.
Ma'am, your screen is visible.
Yeah, thank you. Okay. So first, myself, I'm Hemavathi, scientist in CSIR Central Electrochemical Research Institute, CSIR Madras Complex. It's our institute is located in Chennai. So basically, our major the research program is in the field of electrochemical energy storage devices. Our head office is located in Karaikudi, Chennai, and one of the sister lab is in Karaikudi, Tamil Nadu, and one of the sister lab is located in Chennai. So in Chennai, there are two major researches are going on. One is the fuel cell, another one is battery. And my specific research area in this institute or the custom design of battery management system, battery thermal management system, and development of battery pack for energy storage and the electric vehicle applications. So these are all the brief introduction about myself and our institute. So coming to the point, I'm just going to share about a few knowledge in energy storage and battery management system. So basically everyone knows till about a few years ago, we thought that electricity cannot be stored and it needs to be consumed when it is generated. But now the times are changing. Today's electricity can be stored in megawatt scale level, and thanks to development made in storage technologies and solutions. So these energy storage applications are increasingly becoming viable around the world. And presently the smart grids are expected to be the biggest achievement of the 21st century, and the energy storage technologies are going to be an important part of it. And we can classify these energy storage technologies into the broadly we can classify into the mechanical, electrochemical, chemical, electrical, and thermal. So these are all different energy storage systems, and this is the present and future of the energy storage technologies. So there are a lot of researches are going on in each and every field. And here in this lecture, I am going to give you very elaborated portion. I am going to cover the electrochemical energy storage like batteries and battery management system. So before going to these energy storage, just I am giving some overview about the each and every energy storage systems and where we are using and what is the merits and demerits of these technologies. So basically, like globally, you can see nearly the 202 gigawatt of grid energy storage systems is there, and nearly 135 gigawatt is pumped hydro. Okay, and remaining you can say the rest of the 2677 megawatt being the new energy storage technologies. And first we see about the pumped hydro. This pumped hydro is the most successful energy storage system due to their fast response and storage capacity. And the proven technologies, pumped storage hydro has been the proven to be the excellent reserves. And you can see what's the basic concept of the pumped hydro is two water reservoirs at different elevations are used to pump water during off-peak hours from the lower to upper reservoir. This is called as during the charging condition, and the water flows back to move a turbine and generate the electricity during the discharging conditions. So the main merit of this technology is it's their long lifetime and stability. But still we are facing the problem means the technical and commercial risks have been prevented the large scale adoption. And the next we see about the compressed air technology. So compressed air technology, it's based on the conventional gas turbines and stores the energy by compressing air in an underground storage cavern. So here the electricity is used to compress the air, and when needed the compressed air is mixed with the natural gas and burned and expanded in a modified gas turbine. This turbine produces the same amount of output power as a conventional gas turbines, but you uses only the 40% of the gas. So that is the main concept of this compressed air. And you can see the main advantage of this technology is have a larger capacity, but disadvantage maybe the demerit, maybe we can say it's like a geographic limitations of the location. And the next flywheel. Flywheels, like everyone knows, it's like a rotational energy is stored in the large rotational cylinder where the energy is maintained by keeping its speed constant. So, and also we will use a transmission device. So this device is used to accelerate or de-accelerate the flywheel by supplying or and extracting the electricity. So for example, when the speed will be increased, the higher amount of energy we can store it. So that's the main concept of the flywheel. And now where we are using means presently we are using the flywheel in space application and grid application also we are now presently using on it. In other countries they are presently, for example US, they are using this technology for grid energy storage. And the what's the merit means is have a long life of this technology and very less maintenance requirements and excellent cycle stability. However, it's a high level of self discharge due to their that friction resistance and bearing losses. So due to these reasons, it have a high level of self discharges there in this flywheel technology. And next we see about the electrochemical technology. So on the electrochemical technology, like it's like a very presently in our India, it's a very hot topic, and we are using everywhere in all the applications. This electrochemical technology part is there. So electrochemical technology, what are the electrochemical means, what are the categories are there means basically rechargeable batteries and flow batteries. So rechargeable batteries, there are lot of there are different batteries are the lead acid, nickel, cadmium, lithium batteries, sodium sulfur batteries, and flow batteries, redox flow battery. So these are all batteries technology. So maybe the upcoming slides we are going to see about more about these technologies. And basically the batteries have a distinctly different market segments because of started with appliance and ended with grid. Appliance means like we are using for electric and electronic devices, and second we are using in EVs, and third we are using in home applications and megawatt scale grid integrated applications. So everywhere the batteries are there, and requirement of each of these domains being very different, like the size, the need of the size, capabilities and technologies also can be different. So the different technologies can and will coexist in battery technologies. However, this needs to mature to higher efficiencies and capacity, because of still there are a lot of researches that are going on in batteries to increase the energy and power density of the batteries. So still because of each and every chemistry, so there is some demerits. So again we are moving into the new chemistry. So there is again and again there are a lot of researches are going on to increase the efficiency of the batteries or capacity of the battery. So the now next we see about the chemical. So chemical energy storage systems is everyone, it's like a very, this is also now present a very hot topic in our India, the hydrogen based storage system. So the very famous technology is fuel cell technology. So the next we see about the electric energy storage systems. So electric energy storage system, there is a double layer capacitor and superconducting magnetic coil. So this double layer capacitor, like maybe we can call as a super or ultra capacitor. So first in like maybe conventionally, maybe in it was invented maybe 1970s maybe we invented. It's provide the backup for computer memory, and now we are using in this type of the supercapacitor we are specifically using in space applications, aircraft. So there we are specifically using because of it has a very high power density. Okay, that's a major merit feature of this supercapacitor, and it has a very long life and can withstand lakhs of cycles. And next is superconducting magnetic coil. Superconducting magnetic coil is like a, it's a like a, here we are using a it has a one superconducting coil and a cryogenically cooled refrigeration system that once charged stores the energy in the magnetic field, creates in the coil for an indefinite period of time. And this is also a few of the countries they are using for grid application, but it's still under development only. And the next, thermal storage. So thermal storage means like here basically what is the base means the system use the cold water or hot water or ice storage to store the heat and the use for later. So these are the efficiency of the thermal management system is based on the which type of material we are using. And the best technologies we can say as a solar thermal technology. So because of these technologies are very important for integrating the large scale renewable energy and can be used as the reliable and dispatchable source of energy to balance the both supply and demand. So therefore these are all different technologies, and there are a lot of developments are going on all the technologies, because of each technology have a the specific features is there. So definitely we need all the technologies in our future concern. Okay, then so it's based on these all the technologies we are like classifying. It's based on the power, energy, and discharge time of discharge time. So there are three parameters we are like classifying. It's based on all these energy storage technologies. So you can this is like you can see the range of storage devices is shown in this picture. So this suitability of these energy storage system source for a particular discharge time frame. This particular discharge time frame is determined by its power density and energy density. So first, what is power density and energy density? So basically, power density refers to the energy storage technology's ability to provide the instantaneous power. So, for example, a higher power density indicates that energy storage or the technology can discharge the large amount of power on demand. If energy density means, energy density is the ability of that energy storage system to provide the continuous energy over a long period of time. If the particular device or particular technology have a high energy density means it can discharge the energy for longer period. So that's the main difference between the energy density and power density. Okay, and basically these all generally these all energy storage technologies. So few energy storage technologies with have a highest power density means it tends to have lower energy density, and few of them have a highest energy density, it tends to have a lower power density. So there is some some competition also is there. So for example, you can see because of this quality, how we can do this quality means the quality gives rise to division of this all the technologies into the categories based on the discharge times. For example, you can see the short discharge time resource, like we can discharge for the seconds or minutes. Okay, so in this the particular portion, the particular portion, the energy to power ratio is less than 1. So what are all the technologies dominated by this portion, like this period means, like we can say the double layer capacitor, that is called as a super capacitor technology, and superconducting magnetic energy storage devices and flywheels. So because of these all these energy storage devices have a high power density, but the energy density is very less. Okay, so you can see this portion. Okay, and that's why we can use it for we can use it for very longer period. It will give the very high amount of the power within a short span of the time. And next to the category, we can see the medium discharge time resources. So discharge from the minutes to hours. So in this particular period, the energy to power ratio between 1 to 10, and this category is denominated by the this category is dominated by the batteries. Okay, particularly batteries, and all the batteries, we can say the lead acid, lithium battery, sodium sulfur, and sometimes the flywheels also will come into this category. And the next we see about medium to long discharge time. So medium to long discharge time means we can say hours to days. Okay, so in this category, the power energy to power ratio between 500 maybe we can say the 30, and this include pumped hydro storage, compressed air energy storage, and redox flows batteries. And comes to the next final one is a long discharge time. Long discharge time means we can say like days to months, like from one season to another season. It will provide the energy, it will store the energy in one season, like for example summer season, and it will provide the energy into the winter season. So that type of energy storage devices are like a hydrogen based energy storage device and a synthetic natural gas. Because of these devices will store the large amount of energy in summer month from the solar, it's based on large amount of solar power on the grid, and significantly because of solar power, we will get very significant less in the winter condition. So it store the large amount of the power in the summer months from the solar power, and it will provide the back into the electricity in the winter seasons. That is the major one season to next season. It provide the energy storage um, resource. And this is the the different technologies like where it should be suitable. This is we seen here. And the next we see about the what is the global market scenario demand, particularly from 2016 to 2027 of all the all the energy storage technologies. So you can see in 2016 we can see the 19,927 like a megawatt is like we may be consumed, and maybe we can see the demand also during that particular time. And it should be expected to grow at a compound annual growth rate from 16 to 27. So growing demand, this demand say everything is based on the end user. Okay, end use sectors only. For example, medical, everywhere we are using the energy storage devices, medical, industrial, marine, telecom, data center. So everywhere it's expected to drive the demand for the energy storage systems over the forecast period. So therefore, this trend is expected to positively influence the energy storage industry landscape. So whatever the demand will be increased, definitely the generation also we need to be increases. So based on this demand only, the energy storage landscape, that is energy storage industry landscape also will positively influence it. And next, we see about the next we see coming to the point battery energy storage system. So before we are see about the battery energy storage system, first why in our India the presently the last few years, so presently we are more focusing on the more focusing on very like hot topic like this battery, particularly lithium ion battery technology. So why we are more concentrating, or why the lot of researches are going on, is the basically the basic point is we have to reduce the pollution. That is the basic that is a first basic point. Because of India was ranked nearly fifth in world most polluted countries in 2019. And the present scenario, we are using the internal combustion engine vehicles. So you can see in our the vehicle on Indian roads, there are different like categories of vehicles are there: two-wheeler, three-wheeler, four-wheelers, buses, trucks. There are different vehicles are there. Okay, particularly in our India, the more dominated vehicles are two-wheeler, because of nearly 79% of the vehicles are nearly two-wheelers only. So these typical passenger vehicles nearly emits about 4.6 metric ton of carbon dioxide per year. So everyone knows like carbon dioxide, what is happening, why this, what are the how it started with the carbon dioxide pollution. Everything we basically we knows all the basic things. So this carbon dioxide, basically burning of that petrol or gasol will release the carbon dioxide. So it will affect our atmosphere condition. So this is we can see in our day-to-day life. So due to this due to this reason only, we have to like focusing more the electric vehicle technology. Because of this is an obviously more for a future transport, and it will reduce the emissions that contribute to the climate change and improve the public health and reducing the ecological damage. Also, sometimes we can charging this EV using renewable energy also. For example, solar and wind, which also minimize this emission even more. So therefore, the EVs, the very important key component in EVs is the rechargeable battery, particularly the lithium ion battery technology and more essential device in electric vehicles. Okay, so so therefore lithium ion battery more essential in electric vehicles and energy storage systems. So the next we see about the battery energy storage system for grid application. So this is like some schematic picture for a grid application, how we are like this is some we can see the architecture how we are designing the battery energy storage system for grid applications. So we can say there is a long history of integrating batteries into grid application, and while this battery energy storage systems currently account for only a small portion of energy storage within the grid, they can see great growth recently due to their high energy density and efficiency. So therefore, more grid applications have suitable for the battery energy storage systems, and while performance and life, everything it should be continue to increase. And also one more why we choose this battery energy storage for grid application means these are all able to react to grid demands, and but also have the capacity to function over longer duration and have a wide range of storage and power capabilities. Due to this reason, this is more like adapt to the grid application. And now you can see the major the key components is the battery, and next battery pack, and the very important the control device BMS. These are all the functions of the BMS. And first one by one we will see it. So here the first the batteries. So due to its technology maturity, first we used in grid application lead acid chemistry we used, and has been there is a lot of has been the most widespread among large scale battery energy storage system. However, there is a significant advancement in the newer battery chemistries has allowed for a wide range of battery options for new storage applications, and has increased the robustness and functionality of the batteries within the electric grid. So you can see the last 5 years. So last 5 years, there is a the pilot scale battery energy storage system projects have been undertaken for many new chemistries. Particularly, we can say the lithium ion battery, and first the sodium sulfur battery. Then due to after that we entering into the lithium ion batteries. Lithium ion batteries, there are different cathode chemistries are there. Like from that we there is a new there is a the present also there is a under like the future technology also it's based on the lithium only. So we can say the lithium titanic battery, lithium iron phosphate battery, and NMC battery, and LFP battery. So there are a lot of chemistry batteries we are using it. And what are the like conventional batteries are nickel cadmium, like uh, nickel cadmium batteries, lead acid batteries still we are using, but lithium cadmium battery, these are still we are using for very like portable application, very small power application we are using on it. And what is the future or under development technologies are sodium ion batteries, lithium sulfur battery, lithium air batteries, and we can say the solid state batteries. So there are different batteries are presently going on it. So for particularly for grid applications, there are different chemistries we are looking on it to improve or to give the more demand or more storage for the grid applications. And next the next important key factor is BMS. BMS is like a battery management system. So this basically this energy storage system requires the BMS. It's like a heart of the battery pack. Basically, we can call BMS is the heart of the battery pack. Is to monitor and maintain safe, optimal operation of each battery pack, and a system supervisory control to monitor the full system. So that is the what are the features of the BMS, or like we have to do the state estimation, cell balancing, and production monitor. So everything will do by the battery management system. And we can say furthermore we can say like even under normal operation also, the battery packs of this battery energy storage system will degrade during cycling, because of when we are using continuous elements, definitely it starts to the degrading. So this degradation, okay, basically why this degradation is happening. So this degradation is happening by if you are extreme charging patterns, like if you are do like the charging extreme means like fast charging patterns. So because of every chemistry or every cell have a the standard C rate, standard current levels are there. Okay, so we have to use that standard. How we can found this current levels is based on the cell data sheet. Okay, so when we are providing the more current, when we are providing the more, when we are charging the battery in higher level of current, definitely the battery start to degrade. That's the main first point. And second point means everyone knows if current will be increased, definitely the temperature also will increase. So increase the current, and after that overcharging, undercharging, and we can say over voltage limit, under voltage limit. So there are we can say the all the abuses, we can say the mechanical abuse, thermal abuse, and electrical abuse. So these are all the abuses. Finally, it's giving the result of thermal runaway. Okay, so therefore the basic BMS definitely it's needed, which control the battery pack only to meet the power demand, and that is the basic BMS work. But if coming into the advanced or smarter BMS, it's like a model based BMS, which can predict and reduce the causes of degradation and improves the performance of the system. So that is the advanced BMS feature. And this type of predictive and adaptive BMS based on the models are especially important for like the battery system. For example, large battery packs for applications such as electric vehicles and grid integration. So there we are using definitely advanced BMS to predict the future lifetime of the battery. And so these are all responsible of the BMS. And also this BMS is responsible for the safe operations, like thermal management, operating between safe current and voltage limits, shutdown on detection of the fault. So these are all come in the safety portions. And the state estimation, like we have to do the precise state of charge estimation, and parameter estimation like a state of state of health estimations, and how much time is remaining depending upon the applied load profile. And next, very other one more important feature is cell balancing technique. So the cell balancing technique is like a very important feature to balancing the energy level of the each cell in equal level. Okay, for enhancing the battery life. Then next, you can see this is the like the two key components we seen here. And in large system, okay, basically this is the we seen about one pack and BMS. So basically for if megawatt level, if you are seeing means it's like a very large systems. So in large system there are many battery packs with the individual BMS will be combined to create a large capacity battery energy storage systems. So here you can see that the supervisory system control. So therefore this battery system, it's not directly connected to the grid. It should connected through this supervisory system control. It's like an interface. Okay, so the supervisory system control and this complete energy storage system is the this is the interface between the grid and BMS. So this is the interface because of we are connecting the battery to the grid through the BMS. So it's to the interface. So first it will do the all the real-time computer control. Then after that only it will it should be connected to the grid. So this is the we can call as a data acquisition. So here the monitoring control system. So everything is happening here, and the information about battery pack is conveyed from the BMS to the this system supervisory control. So sometimes, for example, when the grid demands power to power, when the grid, for example, when the grid demands power to be supplied from the batteries, so this supervisory control chooses the optimal protocol for releasing charge while accounting for both the current state of the batteries and the grid demand request. So that is the main progress of this one. It will check whether the battery have a charge or not. Otherwise, what is the demand of the grid? So everything it will check based on that only. It will provide the output. Sometimes this protocol, the same protocol, will call power from the individual packs in order to meet the grid demand, grid power demand. So during certain periods, the required power profiles of batteries will be more flexible, and this storage system can have a more control over the charging pattern. The best example we can say For example, everyone the peak shaving condition, peak shaving application, the discharge power is heavily constrained, but the charging power can be chosen based on the needs of the storage system. So therefore, here the individual BMS can run optimization routines to come up with the best charging profiles. So these charging profiles can be communicated to the the supervisory control system, so which can control the power input from the grid. So for when determining the performance of the storage system, in addition to the BMS and this control, this supervisory control, and also we are coming into the power electronics portion. So this power electronics which connect this system to each other, and the grid must be taken into the account. Basically, what is the purpose of this? All the power electronics means like it allows the bidirectional power flow from like a power flow of power to and from the grid. So the way these individual pieces are structured, and they created a here like we can say the schematic or a hierarchical system architecture will influence the efficiency and operations of the entire system and can aid in the control. So this is the complete the because of that is a the difference is there because of the battery energy storage we are using in everywhere, started with low power application to grid, but there is some protocol differences there based on the power requirement. Maybe you can see the e-vehicles, we are not using this much high megawatt level backpack is not required. So when you are thinking about for grid application, it's required high a megawatt level plant is needed to store the energy. So therefore, the way of the architecture is different for each and every applications. So now the next we see about the battery's history. So how the lithium ion battery came. So what is the evaluation of the battery technology? So everyone knows the American first which battery first the American scientist the Benjamin Franklin first he used the term battery, and he did a lot of experiments with electricity using a set of linked capacitors. Okay, and the first true battery was invented by the Volta. That's why we also call as a voltaic cell. So this is stacked disc of copper and zinc, which separated by the cloth soaked in the salty water. So the most common primary battery is the zinc carbon battery. This is the first the inverted battery, and you can see these are the alkali batteries we can buy from the we can see in the market also. And the next that we can see the lead acid battery. So this is one of the most enduring batteries, and still we are using, and it should be still we are using the technology you can see in still in our internal combustion engine cars today. It is the oldest example of the rechargeable battery. And apart from this rechargeable battery, we can say the nickel cadmium battery and the nickel metal hydride batteries. So these are all also the rechargeable batteries. And the next these are all like we can say the based on each and every evaluation is happened the basically due to the to increase the energy density of the battery. Okay, because of this all the conventional batteries have the energy density is very less. So if you are moving into the very high voltage or high current or high power application, definitely we need a more high energy density cells. That's why there is a evaluation is happened. And today the batteries come in the range of sizes from large megawatt sizes, which stores the power from solar farms or substations to guarantee the stable supply in the entire city, like entire village or city we can say it. And the finally you can say everyone knows the Nobel Prize winner, like the Professor John Goodenough. He invented a new type of lithium battery. So here the lithium would migrate through the battery from one electrode to the other as a lithium ion. So this is basically lithium is the one of the very lightest element in the periodic table. and it has the one of the largest electrochemical potentials, and therefore due to this combination it produces the sum of the highest possible voltage. Because of these are all battery, the single cell voltage maybe it's very less, but lithium ion battery somewhat now they increase. So basically now we are using the nominal voltage 3.7 volt, and now there is a presently a lot of chemistries we are using it now, they are increased the voltage level presently. Okay, so then now this is the the brief introduction about the evaluation of the battery technology. And next we see about next we see about what are the terminologies basically we are using in the battery field. So first, how we can call the battery spec. If you are more, for example, if you are going to purchase one battery, we will say we need a AAA battery, AA battery. This is basically we will say. Okay, for AA battery means they will give, you can use it for your clock somewhere. So this is the basic notation we are using it. Then come, but basically the if OEMs if coming to the lithium ion battery, what are the specifications are there? And if you are building the battery pack, definitely you know that spec, major spec. There is a two spec is there. One is the major and is the minor specs are there. Okay, at least you need to know the battery voltage and capacity. That is because of because of the each because of there are different categories of the batteries are in lithium ion technology. So definitely we need the each battery have a different capacity, different voltage levels. So definitely the battery pack OEMs or companies, they knows they are going to build the battery pack for specific applications. They know, they needs to know about the data sheet of the cell. Okay, uh, so first is ampere hour. So ampere hour is basically, hello. Okay, so ampere hour. So ampere hour is basically it's a basic denotion, or basically we denoted in the battery in terms of ampere hour. So it's like a capacity of the battery. So for example, we can call it as a 1 Ah. So 1 Ah battery means, for example, drawing a 1 amps current from the battery for 1 hour. So that's called as a we are 1 Ah. And next the anode. So this is anode is like a one of the electrode material in the cell, like a battery. So it's like the electrode on which oxidation process will occur, which release the electron on discharge. When the battery on charge, the anode is positive, and discharge turns the anode to the negative. And next we see about the absolute state of charge. So state of charge is how much energy or how much charge is stored in the how much charge is available in the battery. Okay, basically you can see you can see in the um, power bank mobile, so there you can see how much percentage it will show. That is called as the state of charge. And battery life cycle. So battery cycle means how many charge and discharge, how many numbers of charge and discharge we are doing it. Okay, so that is called as a number of cycles. This parameter, so for example, this cell how many cycles will support, this is will given by the cell manufacturer, and this value, maybe this number of times, how many times we can use it, maybe you will get it from the cell data sheet. Okay, and also sometimes if you are buying one application, if your vehicle or any other battery operated any device, if you are buying means they will give the battery warranty also. So that is based on their calculation, maybe how many times you can use it, like that. Based on that calculation they are giving the number of years warranty. And next we see about the BMS. So I already said about BMS is the it's used to protect, monitor, and predict, and estimate the battery performance and characteristics. And the next battery capacity. So already said the ampere hour, battery capacity. So both are same only. Then next we see about the cathode. So one the first the another one more another component in the battery is in the cathode material. So which do the reduction process take place by absorbing the electrons. So during discharge the cathode is positive and this will reverse on charge. And next to coulomb, everyone knows it's like a unit of electric charge. So 1 coulomb equals 1 ampere second. So this coulomb is basically we are the one of the method is to estimate the state of charge called as a Coulomb counting. So there we will use this Coulomb counting technique to measure the state of charge in the battery. That is a very conventional and traditional technique to measure the SOC. And the next we see about the C rate. So C rate is the very important term in the cell or battery. That is, we have to fix on it based on the data sheet only. Okay, because of the cell manufacturer will provide the standard C rate, rapid C rate. Okay, so the standard C rate is called as a continuous current rate. Okay, you can use maximum that much current only. You maybe charge or discharge the battery. Okay, for example, the 500 mAh battery, if you are charging or discharging the battery, if you are charging the battery C/2 rate means the current is 250 milliamps. If you are discharging the battery to C rate means it should be 1 amps. So this is not decided by us. This is decided by the cell manufacturer. Okay, if you are using, maybe if they gave 1 amps, but if you are using the 5 amps, if you are 5 amps, if you are discharging the current from the battery means what will happen means sometimes it will degrade the performance, and your life cycle also will reduce it. And if you are using more current means, if you are discharging current from the battery more means, definitely the short circuit will happen and it will be damage the battery. Okay, so there is some privilege also they will provide it. So you can use the continuously, you can discharge the power 1 amps, and you can rapid discharge. Rapid discharge means like they will provide a few seconds, you can use up to 5 amps, like the peak power maybe you can take it. But apart you can apart from above the 5 amps, it's not safe level, safety, how can we say, like in safety level, that is not recommended. You can use 5 amps also, but what will happen means, if you're using the 1 amps means you will get the 1000 cycles. If you're using the 5 amps, you will definitely not getting the 1000 cycles. Cycles will have definitely reduced, maybe 500, 600, like that only you will get it. But above the 5 means is not recommended in the safety level. Definitely the cell will be damage. That is the different categories are there. And temperature also the same thing. If you have to, there is 3 different temperature levels are there. One is the optimal temperature range, another one is like you can see the aging temperature level, another one is a safety level. Okay, so the next cycle life, I said number of cycles. And the next electrolyte. Electrolyte is also one more the key component, and it will provide, it is this is the conducting material, and it will place it between the positive and electrodes of the battery. And next is energy density. Energy density and gravimetric energy density. So like it's like a whatever per volume and whatever per kilogram. So it's like a mean of the how much amount of the energy of a cell holds in the weight. That is called as the energy density. Specifically power density also the same thing. Okay, so why the lot of researches are happening means to increasing the energy density of the each cell. Okay, because of if one cell have a more and more energy density means we can reduce the number of cells in the pack. That is the main concept we have to increase in the, because of if you are using the more and more cells in the battery pack, because of, for example, grid application, you can see it's a megawatt level. Okay, so if you are using the very small energy density of the each and cell means it will be increased in the cell level, like it will be, you have to use a 10,000 to 20,000 batteries, you need to use it. But if cells have a more energy density or more power density means the number of cells will reduce, and it will be safety and performance wise it should be very good, and maintenance wise also, because of sometimes if more cells, if because of for megawatt level, definitely you have to develop the cooling technology. Definitely the heat will be definitely it produced, so you have to develop the active cooling technology. So active cooling technology means it should be active cooling means the main concept of the active cooling is to operate this active cooling technology also you need the external source. Okay, so it will increase the cost of the total plant. So that's the main portion. That's why we are doing all the more and more the development is happening in the present. And next we see about the relation. So there are different batteries we see. So what is the relationship between these batteries in terms of power and energy? So you can see in this picture, we can say Regan plot, and you can see the, like, for example, started with lead acid, and the lithium ion and lithium metal batteries is have a higher specific energy and a higher specific power compared with the other batteries. So we can use the battery, lithium ion battery, for longer runtime and with the higher current. So that's the major point here with respect to the specific power and specific energy. So therefore, the lithium ion batteries is preferred choice for many application because of high volumetric as well as the uh, energy density. And the next we see about the why lithium ion battery. So from all these concerns, the previous concerns, uh, why we are choose to lithium ion battery means the first point, higher energy density. So per kilogram, that's the first comparing with the conventional batteries. And the second point is a longer cycle life. Maybe you can fill it comparing with the lead acid batteries, you can see the life cycle. Maybe they will provide it nearly 5,000 to 7,000 life cycles. Presently they are providing for lithium ion batteries, so that's why this is a very long cycle life. And next is a deep discharge. So we can do the deep discharge because of the lead acid, we can't do it. Okay, but you can do the deep discharge, but the performance and safety wise is not recommended presently. Okay, but because of, if you are completely, if you are deep discharging the battery, then after once charging the battery means it's take a more time, and we have to also provide the very small amount of the current to take the battery voltage or battery energy level into the norm, some cutoff level. Then after we can provide the higher current to charge the battery. Okay, so that's why basically this performance and the safety mentions, we are the DOD of the lithium ion battery we are keeping on 80%. And the next is highly efficient in storing and returning energy. So then next, fast charge. So fast charge, there is a lot of in chemistry level and in BMS level and charger level, there are lot of R&Ds are going on to take the fast charging concept, because of the particularly this fast charging concept is required for the EV. Okay, so in our India, we want to provide the transition from internal combustion engine to the electric vehicle, means a major problem presently because of EVs came. There are a lot of developments came, EVs came, and you can see in our on-road also, we can see the lot of two-wheeler, three-wheeler, even four-wheeler also. Few of the four-wheeler also is like it's there in our on-road EVs. But what is the major problem we are facing? Means the charging. There is a common charging infrastructure because of, like, if you are taking the two-wheeler, so two-wheeler, there are a lot of brands are there, like Ather Energy and Bajaj, TVS. There are different two-wheelers are there. So each two-wheelers have their own specification. Their vehicle has a own specification. The battery pack also their own. There is not a common, any architecture is not there. So they have a own their specifications. So everything is different. So battery pack, if you are taking, means the capacity, voltage, and the power level, everything is different. And batteries also, the very important concept is batteries also is different. So due to these reasons, uh, we can't we don't have a common infrastructure. So you can see, if you are buying one two-wheeler from the particular company, they will provide they will provide a charger for, you can charge it, you can use the charger in your home. So in night time you can charge it, and daytime you can use it. Okay, and if you are sometimes, you during emergency condition, if you want to go for a very long trip, means sometimes emergency, so that time somewhere the charging infrastructure, maybe their charging points are there, you can use the charging point for that particular application, that particular vehicle only. You can for example, the Ather Energy charging point is there, means you can use it, that Ather Energy charging point for only for Ather Energy vehicle, not for Bajaj. So Bajaj have a their port is different, and this vehicle port is different, and the specifications also different. So this is a major problem we are now facing on it. But anyway, the government also looking on it presently, how we can provide the common architecture, common infrastructure to charge all the vehicles in the uh, like common place. Okay, so that is we are particularly looking on it. And second is common architecture infrastructure is needed. And second very important point is fast charging, because of if you are filling the petrol and diesel like within a maybe seconds to minutes, but EV is not like that. So we are working on it. So it's maybe it will take a more years to come into the India of the fast charging technologies. But it's still there, but it will also take a fast charging still it's take a 20, I think 30 to 45 minutes. So few vehicles they are charging the battery. It takes it will not complete the it will not 100%, it will not completely charge the battery. 80% of the battery, like SOC 80% only will we can fill it in that 30 minutes, and remaining 20% it will take a more time. Okay, that is called as that is CCCV technology they are using. And next is a flat discharge curve and slow low self discharge. You can store these batteries in very longer period also. So definitely the self discharge will not be happen in it's not a very high, it's very low self discharge. And maintenance free, non toxic, and no disposable problems. So these are all like why the lithium batteries choose the present conditions. Then next we see about how lithium ion battery is what is the working principle of lithium ion battery. So the battery pack, basically you can see the battery pack basically is made up of several individual cells that are connected to one another. So you can see each cell. So for example, each cell have a contains there are different parts are there. One is the positive electrode, it's called as a cathode, and negative electrode is called as anode, and liquid electrolyte and separator. Okay, so for example, when the lithium ion battery, if you are in your mobile application is there, so in your mobile phone is powering, if you are basically using on it, particularly on that time, the positive charge lithium ions move from a negative anode to the positive cathode, and at the same time the electrons also move from the anode to cathode. So they are moving through the electrolyte until they reach the positive electrode, and there they all the ions will be deposited. So when you want to charge the battery means it's like exact opposite process happens. So here the lithium ions move back from the cathode to anode, and the electrons move from the electrons also move from the anode to cathode, and therefore there again the ions will be deposit on it. So once again we have to discharge the battery means again the process will happen it. So this is the basic working principle of the lithium ion battery. And what are the like chemistries we are using in the cathode materials are the LCO, NCA, NMC material, LMO and LFP. And anodes are graphite, like carbon and LTO. And now we see about what are the cathode chemistries. So because of these chemistries, okay, the few chemistries practically is proved, and it should be practically proved in our Indian condition, and we are using in presently in all the applications, grid and energy storage, sorry, grid and e-vehicle applications. So first the initial level of chemistry is the first initial level of the chemistry in lithium ion batteries, lithium cobalt oxide. So it this is the what is the specifications of this lithium cobalt oxide means it is this type of cathode material based batteries have a good specific energy. Okay, but the problem is it's very poor, like maybe we can say very low in specific power, and safety wise also, because of the due to the cobalt content, the safety wise and lifespan also it's very poor, and performance and costs are moderate. So that's why these chemistries not maybe in initial level we used, but it's not presently due to this copal content, we are not preferred in practical applications. So therefore, now we are mostly using the NMC chemistry. This is called as a nickel manganese cobalt. Okay, so here the cobalt contribution is very less. Okay, so nickel and manganese contribution is very high. So therefore, this NMC chemistry have a everywhere you can see these all important specifications should be good and moderate. Okay, you can see specific energy also very good, and power moderate, safety moderate, performance moderate, lifespan is also moderate, cost wise also it's moderate. So basically that's why it's practically proven, and where we are using means in all the e-vehicles we are using the NMC chemistry. It should be very suitable. Okay, and coming to the point, the next important practically used chemistry is lithium iron phosphate cell. So this, for the major advantage of this phosphate cell is safety wise it's very good, and lifespan wise very good, perform and good specific power. But the major drawback in this lithium iron phosphate is the very less energy density. So that's a major drawback. But still we are using in the this type of chemistry in particularly for energy storage applications. LFP is we are recommended because of due to the safety. Okay, anyway the energy density is less, but safety wise and lifespan wise is very good. That's why we are recommended for the for grid applications also. But there are a lot of researches are going on how we can increasing the energy density of the LFP battery, because of comparing with all the chemistries, this is very safety wise it's good. Okay, so the more research happening in this chemistry, how we can improvising the energy density of this battery. And apart from these batteries, the polymer battery types also though. So this is like a polymer battery, like it's like we are using a solid electrolyte. It includes also jelly electrolyte, and it's same as like how we are building the lithium cobalt oxide NMC lithium phosphate platform, same thing, but here we are using the solid electrolyte electrolyte. And the next we see about the comparative performance of various lithium based chemistries. So you can see here based on these specifications we are providing a comparative chart like all the chemistries, like each chemistry what is their specific specifications, and what is their merit and demerit. So you can see like here the based on the voltage, first we are taking the voltage basically all chemistries maybe mostly 3.7 3.6 volt, except LFP only 3.2 volt. So that is also one more problem is that the voltage is very less in LFP. Okay, so what will happen now if voltage is very less means if for example if you need a 48 volt, if your battery pack is required 48 volt means if 3.6 volt means you will connect the cells in series, maybe 13 cells or 14 cells. If 3.2 volts, if a cell voltage is 3.2 volt means you have to connect more cells, like nearly 15 to 16 cells are required. So cell requirement will be increased if voltage will be very less means. And charging cutoff limit will be same. If all are 2.4.2 volt, LFP only it's 3.6 volt because of nominal voltage is 3.2. And cycle life it's very good. LFP and NMC it's very good in cycle life, and these are all like moderate. And operating temperature, LFP is safety wise it's very good, that's why the operating temperature is very good, and NMC is good. These both are average level. And specific energy, you can see the energy density of the battery, like you can see this lithium cobalt, lithium manganese, NMC, everything is are like mostly equivalent level, but LFP is somewhat very less, 90 to 120 watt per kilogram. Maybe this data maybe somewhat it's very old data, but now there are a lot of developments happened. And the charge rate you can see here, the LFP and NMC, its charge rate is we can use higher charge rate, and discharge rate also these two chemistries have a higher discharge rate. And all this LCO, LMO, everything is higher discharge rate is there. And thermal runaway, these are all temperature range. So in this temperature range, if we're entering in the cell means definitely the thermal runaway will happen. So these are all like different specifications and how the these different chemistries have how their specifications, and that's why these practically this is also we used this first we initially we use the LCO, and after we are changing from LCO to NMC due to this Gopal content we reduced to here NMC, and there now that's why the preferably we are using the NMC, and LFP we are using in the energy storage applications. And the next we see about the, so chemistry wise we see in the classification in the battery, lithium ion battery, and next the classification is based on the cell form factors. So there is a structure. So what are the structure of the in shape of the batteries, lithium ion batteries are in that. So they are cylindrical, pouch and prismatic. So each have their own specific and specifications. So based on their specifications, we are choosing in their particular applications. So for example, cylindrical cell, the size of the cylindrical cell standard size is 18650 cell. So this is in our India, it's very proven technique, this 18650, and we are using this 18650 cell from started with torchlight like portable application to up to the two-wheelers also. Still we are in two-wheelers, like in our on-road, the few of the companies they are using the cylindrical cell for two-wheeler applications. So so therefore this is a very standard size, and apart from this size there is some developments also is there. So 26650 and 21700, and particularly the Tesla, they are using the cylindrical cell in their car. So there now the standard size is like a 4180, some sizes are there. Okay, so the what is the sizes means it's showing the this what is the difference of the sizes, why we are using the different sizes of the cylindrical cell means to it's giving the more energy density. So for example 18650 in market maybe you can see the level maybe 3Ah. Okay, maximum 3Ah battery only is available, but if you are moving into 21700, 26650 in market up to 5Ah to 6Ah cells are there. So it's just if size will be increased means your energy density also will increase. And steel casing, low manufacturing cost, high specific energy and good mechanical stability. And next we see about pouch and prismatic. So these both cells have, there is no standard size because of cylindrical cell. Maybe we can fix the standard size based on their capacity. We have the privilege, some sizes are there. The each size we can say the range of capacity, but pouch and prismatic cell size will differ based on the energy capacity of the cell. So therefore there is no standard size. Each manufacturer has its own design. So they have their so they are doing their own IP. So they are doing the pattern of the sizes also. Okay, so because of these cells is in market up to 100Ah also is there in each cell. So therefore for example pouch cell has a laminated back, but prismatic is like a aluminum casing. So that's why it will increase the weight of the pack, and it's a very high energy density, good energy density, and commonly these cells we are using in the EVs we are using. So this is preferably we using in two-wheeler in our India, and this pouch cells we are using in four-wheelers, and prismatic we are using in three-wheelers. The next we see about, so once the cell level concept we seen, then now how we are going to make the pack. So when we are connecting the cells in series and parallel connection, it will increase the voltage and the capacity of the cell. It will provide the pack for the for example to meet the power requirement of the application. So first we see about the series connection. So here you can see this is for example ISO, not a 1.2 volt battery is not in lithium ion battery. Just for example I mentioned here. So here we are connecting 4 cells in series. Okay, so first cell has the 1.2 volt, and second cell has, it will adding. If you are connecting the cells in series, the voltage will increase. So 2.4, 3.6 volt and 4.8 volt. So voltage will increase, but current or capacity will be the same only. If sometimes if you are connecting the cells in faulty string, like maybe if all the cell voltage will be equal here, but some of the voltage will be if differ, maybe here you can see 0.6 volt. So what will happen means this voltage will dominate the whole string. So that's why you will get the voltage will be wrong voltage, like 4.2 volt. So what will happen means you will not get the full voltage, will not is possible, and you can't charge the battery pack not completely in full level. Because of this faulty cell lower the overall cell voltage, it causes the early cutoff, and that's why the pack will not will not attain the SOC 100%. Okay, if any one of the cell will completely charge means it will be cut off the complete charging of the pack, and the weakest cell is just most means it will deteriorate the complete the cell starts to deteriorate the complete pack. Then next we see about the parallel connection. The parallel connection, you can see the if here we connecting the 4 cells in parallel. So all the cells have a same capacity, 100 1000 mAh, 1000. So it will increase. If you are connecting the cells in parallel, it will increase the capacity or current of the pack. So 1000, 2000 and 3000, 4000, but voltage will be same. If you are connecting faulty parallel pack means if you are connecting one of the cell, it should be a different capacity or current. For example, you can see the 500 mAh means it is also like a full current not possible, because of due to this condition, it will be the weakest cell will dominate the full string, complete string. Okay, so it will provide the hazard if shorted. Okay, so that's the parallel connection. So therefore, if you are doing a series and parallel connection, before you have, we have to test the cell voltage and capacity, whether if it is we have to do the grading of the cell, whether the cell is in good condition or not. After that only we have to develop the pack and we have to connect the cells in series and parallel. But sometimes there is some the changes will be there, but that should be will compensate by the cell balancing circuit. That's why the BMS is required. In this BMS, we are using the cell balancing circuit. That cell balancing circuit will balance the voltage or SOC of the each cell in equal level. And next to the both series and parallel connection. So for example, I am connecting the 2 cells in series and 2 cells in parallel. It's called as a 2s2p means. So here you can see the total pack configuration. So due to the parallel connection 2000 mAh, due to the serial connection it is the 2.4 volt. Okay, so this is a like a called as the module. Okay, when we are cell, the next level is module. When you are connecting the series and parallel, you will get the module. Okay, the next level is pack. So here you can see the design of the complete battery system for the grid applications. How the process is happening. So first we have to choose the right cell. Okay, first it's based on the chemistry voltage level. So based on that we have to choose the right cell for the specified for the specific application. And next the cell we are connected in parallel. Okay, the stacks of mono cells connected in the parallel. And the next level is we are connecting in the series. So once series and parallel, it's called as the module. The next level is battery pack. So once each module have a interface with the BMS. Okay, the next battery pack means we are connecting the several modules in the series. Again, each module we are connected in the series to for example, if you want the voltage 400 volt means, so each module have a voltage maybe 60 volt means we have to connect the number of modules in series to meet the 400 volt. And next battery system. So now this complete battery pack we are connected in number of parallel system to meet the energy level of the application. So nearly 15 kilowatt hour energy is needed means we have to develop a battery system. So in battery system is consist of the battery pack, and each battery pack is consists of the module, and each module consists of the number of cells. So this is the process how to design the complete battery energy storage system for, or complete battery energy storage plan for the grid applications. And next we see about the battery management system. So first one section we completed, one is energy storage. The next section we are going to see about battery management system. So battery management system. So why battery management system is needed? So here, what are the problems? The main major problem we are facing in lithium-ion batteries: thermal runaway. So the thermal runaway when will happen means there are three conditions. One is the mechanical abuse, thermal abuse, and electrical abuse. So mechanical abuse means any accident or crash will happen. It will not only, for example, if vehicle will meet any accident means it will crash, or it will short the it will damage the battery external portion, external enclosure of the battery means the internal cell also will, some inner micro short will be happen means it tends to the thermal runaway. That is the first major point. And second, you can see the thermal abuse means if sometimes like thermal abuse, the same thing, it will be integrated with the mechanical and the electrical abuse only. So once a mechanical abuse if happen means the some short will be happen, the micro short will be happen in the cell means it started with increasing the temperature. That is also called, we can say, as a thermal abuse. So thermal abuse we can say in different ways. In electrochemistry level also thermal temperature will increase, and we can say the sometimes this type of action will happen also, the temperature will rise. And third is sometimes the electrical level. For example, if a battery will be overcharging or over discharging, or if you are passing the more current into the battery for charging, or if you are taking the more current from the pack from the discharging. So these are all next level of electrical abuse conditions. So these are all tends to the thermal runaway. But how we can control, or how we can predict, and how we can avoid to manage and maintain the this thermal runaway is needed for. That's why we needed the battery management system. So the battery management system, it will be initially will predict and provide the information to the user, and also to control the operation of the cell level and pack level. Okay, so it's to like avoid the cell, it's to entering into the thermal runaway conditions. And the next we see about the main functions of the BMS. So first, the main important function is the protection. So the BMS will provide the protection against short circuit, overload, overcharging conditions, like deep discharging conditions, and overheating. You can call it a over temperature. So these all the productions will provided by the BMS. So it will provide the initial level of, it will provide, it will easily identify the problem in initial level, and it will control, and it will provide the information to the user also, and to stop the charging and discharging discharging operations. So these are all will provide the main functions of the BMS. And second, the main function is performance management. The one more feature, one more important function in the BMS is like a monitoring part. Okay, monitoring and management. So monitoring of the temperature, current, voltage maybe we can cell voltage and pack voltage. So these are all the user can monitor by the BMS, okay, through any communication. Okay, so for example, in EVs means we are using the CAN communication. So maybe if energy storage means we are using the RS485, and different communication we are using to monitor this all the parameters. Like at the same time, this production also we can monitor it, and the power safe mode, and balancing. So these are all cell balancing. So these are all is needed to manage and monitoring the performance of the cell level and pack level. And next we see about the next we see about the state estimation. So state estimation, the main two state estimation is required to monitoring the like efficiency and the performance of the battery, to estimate the efficiency or performance of the battery. So that is called as a state of charge and state of health. So it's basically state of charge, it's denoting the how much charge level is available in the cell. But state of health is like a future prediction, and future and present prediction also. How many, what is the health of the battery, and the first point. Okay, and second is like how many number of cycles still we can use it, or how many, what is the future cycling life of the battery. These are all will estimate by the state of health. So what is the internal parameter is based on the state of health means, the internal parameter means internal resistance and capacity. So these two parameters is needed, you need to measure to found the battery state of health. So these are all, there are different techniques are presently there, methods are there to increase the accuracy of this estimation. And the next stage is like a interface. Like interface means we can say the display, communication, data logging. So these are all additional features how we can storing the data, and in future maybe we can do some analysis to predict the lifetime of the battery. And maybe in real time, so the few every milliseconds we have to monitor the data. So this status, display and communication, these are all very useful interfaces to monitoring in real time of the battery pack condition. And the another secondary functions are like remaining functions are like charge and discharge control, pre-charge and pre-discharge control, contact control and cooling control. So these are all like the very important the major functions of the BMS. Then next we see about the few features of the BMS we are going to see. The first is cell balancing. So the main function of the cell balancing to maintain all the cell voltage in equal level to enhance the battery performance. So cell voltage or all the SOC of the equal level to increase the lifetime of the battery. So basically why this balancing is required means, it will achieve the maximum efficiency of the battery pack, increase the life cycle of the battery pack, and protect the battery from getting permanently damaged. So here you can see in this class there are different levels of waters are there. This is a fully the glass is full water, and this half of the water only is there. There is no water. So this is the like a major concern. I can say here we can say these are all the voltage level in the battery, or otherwise SOC of the battery. Okay, so what will happen is, if I am charging the battery, due to if I am discharging or charging maybe if I am charging the battery means the cell is already fully charged, but this cell will be 50%. There is no charge in there. So what will happen? Immediate cutoff will be happen. So due to this reason, one of the cell only every time during all the charging conditions, one of the cell only again it will be complete the charge, but remaining the weakest cells it will not complete their charge. We can't attain the full charge of the battery, and the weakest cell only will dominate the whole string of the battery pack. So this will what happen means, it will again and again we will do the charge and discharging process, mean it will degrade the lifetime of the battery. So that's that's why the cell balancing is required in the battery. So what are the techniques are there means, active and passive cell balancing techniques are there. So basically passive is we are using in low power applications, because of this is very simple technique, and cost also very less, and very and this technique we are using during only charging condition only, not in discharging condition. And the main problem because of this is the resistor based technique. Okay, we will use the resistor, the switched resistor. We will use it for each cell. For example, if you are connecting the 13 cell in series, so each cell has a switched resistor. So this switched resistor, based on the switched resistor, we will calculate the balancing current. So the range of balancing current of the in passive cell balancing technique, we can use maximum 100 milliamps ampere to maybe 500 milliampere amperes also presently we are using on it. But in the basically milliampere level is the best level in the passive cell balancing current, because of the resistor will provide, because of we are using the resistor. So here the here the voltage levels will be equalized by the energy is dissipated through this resistor. So due to this energy dissipation, heat losses will be happen in the circuit. So that's why we are that's why the cell balancing current we are maintaining like a very low level. Okay, so maximum current level is 100 milliamps is the, it's like a very preferred level, and it should be good actually. Maybe we can say heat dissipation is there, so that's why we are keeping very low amount of the current, and still it's practically provable, and we are using in practical applications in passive cell balancing. Still the two wheelers also we are using the passive cell balancing technique only. And next, coming to the point, active cell balancing. So active cell balancing, here what we are doing, we are using the storage devices like a capacitor, inductor. So what will happen means this will transfer the energy from one strongest cell to the weakest cell. So transferring of the energy only will be happening here, and also this balancing will be happening in both charging and discharging conditions also. So therefore there is no losses. It will be increasing the battery efficiency, but the main drawback is it should be the higher cost, nearly 3 to 4 times higher than the passive cell balancing cost. So that's why it basically preferred for the high power applications. And next, another feature we are going to see about the state estimation. So state estimation, the main state estimations are state of charge and state of health. So state of charge is basically we are using the different techniques. Like first we used the Coulomb counting technique. So Coulomb counting technique, it's like a it's like a integral based of the current. So what is the main drawback of Coulomb counting is the initial level of the state of charge we will chosen by the randomly, because of we can only the user or the person only we have to use the randomly, we need to choose the initial level of the state of charge, and after several training only we can attain the exact value of the state of charge in the battery. So that's the main drawback. And after that there are a lot of direct and indirect techniques also is there, OCV based and voltage, terminal voltage based techniques, and coming to the point, adaptive or model based techniques are Kalman filter technique. So Kalman filter technique, it should be a very accurate technique, but we are presently the Kalman technique basically people are using in practical applications. And the next, the advanced techniques in present in advanced techniques are data driven technique like machine learning, AI. So these are all advanced technique to predict the future estimation or future state of the battery. And state of energy is the ratio of remaining energy to the nominal energy of the battery, and the state of power is the ratio of peak power to nominal power. So these are all we can get it from easily from this estimation. And the state of health is the ratio of the capacity of the aged battery to the nominal capacity of the battery. So basically state of health we can predict from the internal resistance and the capacity of the battery. So internal resistance, capacity, almost capacity okay, but the internal resistance will give a more accurate value compared with the capacity. Okay, so this is for this also there are more techniques are there to predict the state of health, and very best technique we can use the advanced techniques only. For example, this type of ML, machine learning, and AI. So these are all they can what they will do, they will do the analysis of the complete complete analysis of the life cycle of the battery. That is we can that data will provide it, that data will provide you the future prediction of the battery life. So if you have a more and more data means you can predict the life cycle of the battery in different temperature conditions, different C rate conditions. And next we see about the topologies. The topologies, what are the topologies are there? So first is the centralized BMS. So centralized BMS is a very single controller, single board actually. So the single board is connected to the cells through a multiple wires. So everything like all the features will be implemented in a single board. production, and control, charge and discharge control, monitoring feature, communication features. So all the features we are implemented in the single board. And a modular BMS means a few controllers each handling a certain number of cells with the communication between the cells. So like here we are connecting the controller for the each module, and these all controller will communicate with each other. And distributed BMS means it's like a BMS, like this controller, this BMS board installed at each cells. So with only communication cable between battery and the controller. Okay, the basic difference means this is for module and this is for the cell. And next level is master slave BMS. So here one master controller is connected to the slaves and the slaves are connected to the cells. So presently which technique we are using mostly means centralized BMS and master slave BMS. These two techniques basically we are using for if you are like if you are high power, like for example 4-wheelers, we are using the master slave technology. And finally, coming to the point, finally the BMS applications. So it started with mobile and it ending to the grid applications. So it's all the functionality because of mobile have a, it's very like low power application. So some needed, some all no need to implement all the specification. Because of mobile we are using a single cell. Okay, so in single cell means there is no need of cell balancing circuit. The like that we can say for our next level is laptop. So for the specifications of the laptop, the specifications also will add. So if power will be increased, means the specifications also will increase more. So based on that, it started with portable to and grid applications. And these are all our recent developments, like the indigenous. These are indigenous started with the torch, and we did it for up to the 2 pillars. So these are all our own indigenous cell pack BMS. So all our indigenous products. So I'm going to end this presentation. So thank you everyone.
Thank you so much. That was a very wonderful session. I request participants to ask their questions. I have few questions in chat box. Shall I start, ma'am?
Yeah.
Yeah. So one question is from Mr. R.L. Birla. Do you think aluminum air or nano battery, solar and glass battery are going to get prominence?
So solar and glass battery, I am not much about that battery, but the aluminum air battery or nano battery definitely. So definitely it should be a very prominence, and maybe that's why I said there are a lot of future under development and future technology batteries are there. So these are all but based on the application requirement. I said now some applications required a high power, but some application is required a low, high energy. So that's why this aluminum air and nano batteries definitely it has the future development is there.
Okay. There was another question, why the cell size end and central length has been shown differently for cell balancing method.
Why the cell size
In the slides you have shown, one of the slides. It was just for representation or the?
Yeah, I will share the screen.
Yeah.
So the question is cell balancing.
Yeah. This one, I guess.
I don't know. Just repeat it the question again.
I guess the question was on the representation. I guess the cell size looks different. For
this is like a pictorial form, like the energy level of the cells I am telling. Okay, that's why in pictorial we are giving like this is like here this is the full battery, and we are transferring the energy into the here battery. That's why the pictorial form we gave this picture. That's all. Anyway, the battery size will be same only. Okay, just for pictorial form I gave it. Yes.
Okay. Okay. Participants, if you have any other question, you can ask. I have one question. Like, if we have, let's say, some cells are faulty in the system, or they are not fully charged, like you have shown in the battery management, this state of charge and in those slides. So, how does this battery management system exactly points out that cell within that cluster?
Okay, so your question is if any fault will happen, like maybe in terms of any overcharge or overcharge, whatever short circuit. So any fault will happen, how the BMS will predict that fault and how it control the operation. That is your question, now.
Like if we have this 48-volt battery or 72-volt battery, there will be number of cells in series, right?
Yeah.
So how the battery management system will identify that particular cell in
Yeah.
the cluster?
So that's why in BMS there is a like a cell monitoring feature also is there, because of, for example, 48-volt system. So 48-volt system is we are connecting the cells 13 or 14s. So 14 cells we are connecting in series. So we have one more monitoring feature of cell voltage. So we can monitor the each cell voltage in that all the 14 cells we can easily monitor the cell voltage level. So there we can easily point out which string it's like a the malfunction in which string is happened. There we can easily identify and we can separate that string from the battery pack and we can modify it. So that is one of the option in the BMS is there. And second, if any fault, if for example sometimes overcharging or over discharging, sometimes in electrochemistry level also some internal short circuit sometimes will happen. So these indications we will get in initial level in the BMS, like some fault prediction, some alert we will get it from the BMS to the user. And what the BMS will do means it will stop the operation process, whether if it is charging it will stop the charging process, or whether it is discharging it will stop the discharging process. Sometimes during the atmosphere condition the pack temperature will be rise. If for example if a two-wheeler also you take it, we are not using any active cooling technique, just air based technique only we are using on it. So during summer days sometimes the pack temperature will be rise on it. The temperature due to rise due to the atmosphere temperature, at the same time operating temperature also, vehicle operating temperature also. So due to these conditions the BMS will identify it and it will stop the operation. So once the battery will cool down and again start the again it will start the normal operation. So that's the main prediction of the initial level control of the BMS. Actually you are in mute.
Okay,
please unmute.
sorry. So I have another question. Like in this BMS system, for monitoring each cell, do they have direct like a physical wire from each cell that is connected to the BMS system, or it kind of calculates from entire that pack of one line, one cell line?
Yeah. So here the BMS have a we can calculate it both cell voltage also we can calculate, pack voltage also we can calculate. So there is a wires will come from the string. We will connect 14, for example 14 cells will be series, means we will take 13 strings from the cells. Okay. Yeah. So there we will connect it to the cell, so we can monitor the each cell voltage. And pack voltage anyway we will connect the positive and the negative pins, negative wires to the BMS. So from there we can easily calculate the pack voltage. And second thing is BMS also has some some topology to measure the pack voltage. So there are also some monitoring or some measuring feature is there to measure or to estimate the pack voltage. So we can easily cross verify these two, whether BMS calculate pack voltage and nominal V and measured pack voltage. So these two also we can cross verify it.
Okay, okay. One more question from my side, actually. I
Yeah.
wanted to know, like, if there are, let's say, n number of packs in that particular battery, parallel, let's say, slots, and if one of the slot is some cell is getting damaged, or the battery management system is detecting that particular cell in this row is faulty. So, do they have any provision like that will this will exclude that particular line and work on other parallel, let's say, combination? So does any system is there in that battery management system, so that
Yeah.
the system will keep on running?
Yeah. So how we are doing the serious faulty cells, we can identify it. The same thing in parallel also we can identify it. But we can, the BMS, we can, it can identify it. But in future, if you want to modify, means, for example, if you are using the cylindrical cells, means you are using the number of cylindrical cells. Okay, very more multiple number of cylindrical cells. So the problem is, maybe it should be very number of cycles you use to more. For example, 500 cycles, 600 cycles you used to means you used to, and you using BMS, you identified that string. Okay, but if you want to modify, means if you are modifying that string, means again you are going to use the fresh cells in that string. So it will not definitely, because of remaining cells are like somewhat their internal resistance is different, and fresh cell internal resistance is different. Okay, so the cell balancing also is there, but you can see electrochemistry wise it's somewhat different. Okay, the degraded cells, 500 cycle cells internal resistance totally different, and the strings the fresh cells have a different internal resistance. That's why it's not recommended to use it in new fresh cells. So what is the next option, means you have to replace the complete pack. Otherwise we have to remove all the cells, and we can use it for some other low power applications. Okay, so all the fault we can predict it initially using the BMS. That is the option is there. But how we can after that, how we can avoid, means these are all like we have to do it in our manual process only.
Manual. So automatically it does not divert the load to good cells or good rows.
Yeah,
good strings.
for example, if a battery gets overcharging, okay, that should be initially will predict by the BMS. What it will be do, it can easily control the cell voltage level. And if, for example, if you are charging the cell, okay, the BMS just identified, for example, the maximum voltage is 4.2 volt. So the in BMS it has some control level, it has some threshold level also is there. So overcharging, it can allow up to the 4.25. So that it will can easily predict it. And what this BMS will do, it will stop the charging process, and it will start the discharging internally. It will provide the very low amount of the current to discharging the battery and to limit the 4.2 volt. So the few of the things we can control, and we can taken into the normal level. That is, we can do it in the BMS, we can do it. But if damage or any internal short, this will be happen, means we can't we can't just we can see, we can predict only, but we can't do any control. We have to do everything in manual only. And temperature also, sometimes I already said na, if over temperature will be happen, means you can control that on using the BMS. Okay, but the temperature rising like a very high level, it's entering into thermal runaway like that, means what will happen, means the BMS stop the operation.
Right.
Okay, it will separate the back from the application. Because of, if you are not separating the application, means the application also will damage.
Right.
So yeah, so that is, will all the initial precautions will be controlled. Everything will take care of by the BMS.
Okay, thank you, ma'am. There is one more question. Is there a system by which the interruption in the process does not take place even if one or more cells are faulty?
Is there a system by which the interruptions in the process does not take place even if one or more cells are faulty or bad?
Yeah, actually, that was the question, like I asked in some other way.
Yeah, that's
Right.
why.
Yeah,
Yeah,
right,
maybe
right.
I already gave the answer.
Right, right, right. So any other doubts?
Ma'am, good morning, ma'am. Am I audible?
Yes, yes, you're audible.
Yes,
Please
yes.
continue.
Thanks, ma'am, for an excellent presentation.
Thank you.
Uh, I have some questions.
Yeah.
What is solid state battery, ma'am?
Solid state battery, basically I'm not a electrochemistry person, but basically what we will call as a solid state battery means, you can see now presently we are using all our like um, like batteries, NMC chemistry, LCO, all the chemistries we are in that cell we are using the liquid electrolyte. Okay. So now the what is the future technology means, solid state means the electrolyte should be a solid, it's not a liquid.
Based on the type of electrolyte you are using, that name is like that. Okay.
Yeah. Basically, because of if you are basically the thermal runaway, everything is happening in the final after the 70-degree. If you are increasing the cell level, why that fire will be happen means this liquid electrolyte only. Okay, so that's why everything they are the future technologies. Why the solid electrolyte means that we can easily avoid that fire.
Okay. Thank you, ma'am. Now, next question is mine, that which battery chemistry is the most promising for future, as per your opinion, so that we can rely on that in the future? What will the best chemistry, battery chemistry, in your, as per your opinion?
Like now the future technology, the solid state batteries and lithium air battery. Okay, because of that is the future development, lithium air batteries and sodium batteries. Okay, because of sodium batteries, why I am telling the sodium battery means what we are facing in the lithium battery means lithium. Because of lithium, we are we don't have a the source in India, lithium. Okay, so presently in our India, we are taking all the technologies to India. First what happened here means first we developed the pack. First we importing the cell from other countries and we developed the pack, and BMS also we purchased from other country and we are interconnected it, and then after the next level we we just changed our internal combustion vehicle into the hybrid vehicle, and after that full electric vehicle. So there we are connecting the battery pack. So level by level some development happen in our India. So for this all the levels now we have the facility. Now the major thing is cell. Okay, so cell means now the in our India they are developing the cell technology also. So the few of the companies they started to develop the cell fabrication plant. They are going to develop it. So now cell also will come definitely in our India. So now the price also will going to reduce. But the major problem is where we will get the materials, where we will get the chemicals. Okay, so lithium is not still not the source is not available in India. We have to anyway. We have to take get from importing from the other countries. There is no other options presently now. So that's why the sodium batteries now the researches are going on because of sodium is available. Okay, so that's why that is the future technology.
Okay, ma'am. Now another is that we are most excited towards the fast charging.
Yeah.
In my opinion, if you see the fast charging, we are putting the battery under stress. That is, we are providing more current and voltage. Right, ma'am?
Yes.
Right,
yes.
ma'am?
Yes.
So in that way, if you look at the scenario of the battery health, battery is the main heart of the EV. If you see the power where power is concerned. So what will happen on the effect of that fast charging on the battery health, ma'am? That is, I am wondering around that. What will happen to the battery life? Because if you charge the battery in a proper way, then its SOC can be maintained. A very good SOC can be maintained, means voltage level. So with the fast charging, what will happen on that status of the status or battery health? That is my question.
Okay, so if each cell have their own specifications. Okay, you can use up to this current level C rate and standard C rate, rapid C rate. Everything you will be get from the data sheet. Okay.
Yeah.
So now what will happen means, why the presently the lot of R&D is happening means due to this for fast charging only, because of still we are not attained the high energy density and high power density to
Yeah.
adapt the fast charging. Okay, in cell level, because of electronics level, everything we can do it. In BMS we can definitely the BMS definitely will support the fast charging, and charger technologies also we have. But cell, if you are entering into the cell, because of the when you are entering into the fast charging, the first point is cell only. First the cell will adapt or not.
Yes, yes, ma'am.
Okay, because of every other remaining things, everything we have that technology in our India, the fast charging in electronic level. But electrochemistry level, why the lot of chemistries and why the each and every R&D again why we are moving into the new chemistry means that there is only one point is fast charging only. Okay,
Yes,
if you are
yes.
improving the cell energy density and power density means definitely the current also will be increased. The C rate of the cell also will increase. Definitely the fast charging will adapt to into the battery.
That means
Okay.
more work has to be done in that level, electrochemical.
Yeah. You can
So,
actually presently our in India is there actually. And two-wheelers also they are telling the fast charging technology, but they are mentioning that 30 to 45 minutes. It's called as a fast charging.
okay.
Okay, for basically if you are charging in your vehicle in your home means it takes at least 5 to 6 hours it will take. It's a slow charging only, it's called as a slow charging. But the same vehicle you can charge in some other outside, like any common port. That common port is provided by the specific OEM, that specific vehicle OEM they are providing in it. But you can see in Bangalore somewhere is there actually. Okay, so there you can charge it. They are telling you can charge it within 45 minutes, but you can't charge the battery pack fully. It will charge up to 80%.
That's right. That's right.
Okay, so that is they are called as a fast charging. Okay, but still not if basically fast charging in our mind it's considered as the seconds 2 minutes. But it's that's why there are still it will take more time in India to come into the seconds 2 minutes to charging the battery.
Okay. Another question about the sea level, madam. We are always worried about the sea level. So, in how to decide the suitable sea level for off-road because off-road vehicle application? Because I am an agriculturist now. I am working to develop some vehicles for agriculture operations, off-road vehicles. So that's why how to decide the suitable sea level for this application or for any application. How to decide, ma'am? Different sea levels are available for the different vectors. Companies are claiming.
Yeah. That's why I already said if what is happening in charging, the same thing in discharge. Okay, basically how you can define the discharging of the battery pack. It's based on, for example, EVs means it's based on the motor. Okay, so for a motor operating based on the motor power rating and voltage levels, we have to fix the discharge rating of the battery pack. Okay, so each vehicle they are using the different power rating of the motor, and the type of the motor is also different. Okay, so it's everything is based on first you have to calculate the motor rating and motor controller range. So based on that we have to choose the cell. Okay, for example, you want to discharge the battery pack for 10 amps. Just for example, I am telling you 10 amps you need a discharging current. Means if you are connecting the 100 cells in 100 cells, there is a 100 cells 100 cells is there in that. So current should be based on the parallel connections. Okay, so there is a 8 parallel connections is there means we have to calculate for 10 amps you want to take out means so how much each cell will take averagely. Okay, so if it is take 1 amps means that 1 amps will that cell will support or not. It's a standard continuous discharging current or it's a very high level of the current. That should be you can identify from your the cell data sheet. Okay, so in cell data sheet they will mention 1 amps. For example, in cell data sheet they will mention standard discharge current 5 amps. They mentioned means 1 amps is it's supportable. Okay, you can use it up to 5 amps for the single cell. Okay, so this is the way of we have to identify the C rate.
Another thing, so ma'am, regarding the battery temperature, maintaining battery temperature. So what type of coolants they are using for that purpose, ma'am? Or how they are doing the cooling of the battery or maintaining the temperature of the battery?
It's also based on the application only.
Yeah.
For
Yeah.
example, if a low power application, for example, we can say uh, like a two-wheelers, maybe we can say. So there we are not using any
Yes.
particular cooling technology. Maybe we are using this just a air-based technique only. We are
Yes.
using on it. Okay.
Because my application is off-road application, agriculture operation. It needs heavy power and heavy torque also. So that's why I am asking. I have to incorporate the
So
cooling
what is
system.
your application?
I am doing this plowing operation and weeding operation. Means soil interaction operations are there, where we have to move the plows or other equipments to do some soil operations.
Okay.
So that part, heavy battery wattage appear is also required, and also cooling
Then
part.
recommended technique is active cooling balancing. So active cooling technique is very recommended technique.
Okay.
So active cooling we are using for four-wheelers. We are using.
Okay. Is there any company who is dealing with that active cooling?
Companies.
Because if you take as a part of that, nobody will provide. I am also facing in that getting some very good battery packs, but there is always confusion with CAN BMS like this. They are telling C rating also. There are many things are there. Though they are manufacturing the things, they are ready to supply, but as per our convenience or application point of view, if you get the proper battery, means in the good battery having good sale status, that will work properly rather than just taking the or purchasing the battery from the market with all the smart things. That's my question. That's why I am asking for lots of questions.
If you want that separately they can provide or not, means the company what basically that is their own technology.
Yeah.
Okay.
They owned that is the
Yeah. So basically they will provide the product wise, they will provide it with the battery pack like that. Maybe the product wise they will provide, but they will not provide you the technology. Okay.
Yeah.
Because of their own technology, their own IP. So maybe you can do the research like that. Maybe you can do it. Means I don't think so. The company will not provide the separately that technology.
That's right, because my limitation is I can't go for the R&D in battery.
Yeah.
I have to purchase, but that should be suitable for my application.
Correct.
So that's why the many technical points has to be there, so that battery will work properly with that particular application.
Yeah.
What is intended. So that's the thing, ma'am. So thank you very much, ma'am, for you address all of my queries. Thank you very much.
Okay.
Thank you so much. Thank you so much. I guess we have reached a time limit. So thank you so much, ma'am. Thank you for your wonderful session. You have covered a lot of points, including this electrical energy storage.
Sir, can I interrupt you sometime? One not question. To that, can you, ma'am, suggest some equipments for testing of battery parameters? You shown the different parameters are there to judge the battery status. Can you suggest some equipments that can be purchased from the market and used for this battery applications or testing the battery? That is my question.
Actually, these testing equipments are very higher cost.
Yeah.
So, like you want to do like a very major study. Like there is some few equipments are there. It's like there is a lot of parameters. Like very electrochemistry wise, we can do the testing, and electrical wise, mechanical wise. So there are the type of testings are there. Okay. So if you want to do the life cycle test, means there is the battery cell tester is there, like we can call as a cell cycler. Okay. Battery cell cycler. So that equipment will provide you can do the 1,000, 2,000 cycles. You can, whatever, if you are purchasing one cell, So you can
Okay.
cross verify your data sheet, how many cycles they provided. So that much cycles you can test, and what is the performance of the battery, you can test it using that cell cycler. Okay. And in research wise, if we are thinking means there is some other equipments are there. Like that equipment will provide the what is the internal resistance and how much capacity we are attaining for different C rates. And sometimes there is a different testing conditions. For example, if you are charging the battery in CCCV method, but there are different methods are there, like a pulse power driven method, because of if you are driving the vehicle, there are the graph will come, like the voltage and current should be completely pulse if you are giving the more and more acceleration. So that type of cycles also is so every tester is a different tester, so everything will not come in the single equipment. You can check in online, like the battery cycler. There are a lot of leading companies are there. Particularly you maybe the cost is like, if you are choosing the US brand means the cost is like it's coming in the crore. Okay. But if you are choosing the Chinese product means it will be coming in the lakh. Okay.
Is there any manufacturer, ma'am, in India?
No.
Who is developing this type of?
No, it's completely importing only.
Okay. Thank you very much, ma'am.
Thank you so much. We are a little ahead of time, so I will conclude the session by saying the vote of thanks. Thank you, ma'am, for a wonderful session. You took us through various concepts of battery management system. We started with electrical energy storage system, their efficiencies, battery management system, their components working. Then you also explained very well about the terminologies, architecture of battery management system, working of lithium-ion battery, its chemistry, battery types, design and functions of battery system. So it was very wonderful. You also answered all the questions wonderfully. We have learned a lot from this session. I guess all the participants will agree with me. So thank you so much, ma'am. Thank you so much, participants, for patiently listening to this session. I will conclude this session now, and we'll start at 12 o'clock for session number 2. So there are a few questions about test timing. So after third session, we'll begin with the test, and other instructions about the test will be given in the WhatsApp group. So thank you so much. Here we announce the first sessions to be concluded. Thank you so much. I request every participant to turn on the camera. We'll have a screenshot, and then we'll conclude the session. I request host to take a snapshot and just inform after that so that we can conclude.
It's done, sir.
Okay, thank you once again.
I request all participants to fill the feedback form.